Hello everyone. So we are going to be talking about the closure problem and other tensor properties in today's class. So if you remember last class we were dealing with the Reynolds stresses. The Reynolds stress comes about when you average your Navier-Stokes equations. You use the Reynolds decomposition and average out the Navier-Stokes equations. The Reynolds decomposition basic idea is U as a vector, instantaneous, is equal to mean, again as a vector, plus the fluctuation, again as a vector. This is the basic idea of the Reynolds decomposition. You substitute for your instantaneous velocity in the Navier-Stokes equations, you substitute these Reynolds decompositions and then you average out the equations. There is one term that gets left out, which is the Reynolds stresses. As you can see here, this is the Reynolds equations shown here on the screen. On the left hand side, I have the mean substantial derivative. The mean substantial derivative is another form of the substantial derivative where the convective term in the substantial derivative becomes U average, mean of U, dot the gradient. So we are defining this new mean substantial derivative. The only reason why we are doing that is so that we can express the Reynolds equations in the same form as we generally express the momentum equation or the Navier-Stokes equation. So as you can see here, the Reynolds equation shown on the screen here, on the left hand side, I have the mean substantial derivative, like you would have a regular substantial derivative in the Navier-Stokes equations, the acceleration. And on the right hand side, I start by writing out the viscous term. This is the viscous term. Then I have the pressure gradient. But there is this additional term in the Reynolds equations which is not there in the Navier-Stokes, which is the Reynolds stress term. So now if the flow is laminar, this Reynolds stress term goes to 0. This is equal to 0 for laminar. For turbulent flow, it obviously exists, it is finite. Now, just one point about the viscous term, you will see that this is slightly different from how we had written it earlier. The reason being, we have now written it in terms of the strain rate. Okay, so that is del ui del xj plus del uj del xi, and you will see why we do this actually in today's class. So, the viscous term, if you actually expand this out, the derivative of this first term will go to 0 because of continuity. Because you have a del I here and then you have a del xj ui. So since the mean velocity also satisfies continuity, the derivative of this first term will automatically go to 0. So then all you're left with is a double derivative. So you're left with a double derivative, which is how you would see the viscous term. Okay. So now I have this Reynolds term, which is the only thing that is sort of extra in this turbulent equation. And one additional point, the viscous stress stems from the momentum transfer at the molecular level, isn't it? Because viscosity is a molecular property. On the other hand, the Reynolds stress, so you have the viscous stress and the Reynolds stress. The Reynolds stress stems from the momentum transfer due to the fluctuating velocity, which is at the macro level. So this was about the Reynolds stresses. Now that took us to writing it in terms of the momentum flux. And we use the control volume theory to write the rate of gain of momentum, m dot, which is rho u minus u dot n dA. This right here is the volume flow rate. U dot n is the unit normal to the area. So if you have an area, n is the unit normal. And u dot n gives you the volume flow rate per unit mass. So you have u dot n on that side, so that will be a scalar because it's a dot product, and because the momentum is a vector, you would need to have a u here so that you are now trying to find out the momentum in the direction of u. That's what you're trying to do. So the mean, now if you take a mean of this, because we are in the process of taking the averaging always. So if you take a mean of this, the j component, so that is m dot j mean, then what happens is, because this is this term where you have U and U, Ui, Uj. So in index notation, this is Ui, Uj. And then you take a averaging of that, because you are taking the average of the jth term. So I want to refresh your memory in terms of, we did something similar when we took the Ui, Uj mean, isn't it? And that's exactly what you have in the momentum flux. When you say what is the rate of gain of momentum, that is U times U dot N. In index notation, that is Ui, Uj, which is this term here. And when we averaged it out, when we did the Reynolds decomposition of that and averaged it out, what we got is Ui mean, Uj mean, plus in terms of the fluctuating velocity, Ui, Uj mean. And that is what we are writing it out here. So in the last class, I probably did not complete it by showing it, but this is what we have. Ui, Uj, Ui mean, Uj mean, plus Ui, Uj mean in terms of the fluctuating. This is an index notation, so there would be an Ni here to indicate the unit normal. Fine. So then this is your rate of gain of momentum. Now, if you use the divergence theorem, you can convert this area integral into a volume integral, and then you have that as del xi of this part. And it will be a volume integral, so Ni dv. This is coming from divergence theorem. So this right here is what you have in the Reynolds equation, isn't it? This right here is what you have in the Reynolds equation. One of the terms is coming from the mean substantial derivative and another term is coming from here. So what we are trying to say here is the rate of gain of momentum is due to this mean terms and also due to the Reynolds stress term. So that's what we mean by this sentence. So for the control volume V, the Reynolds stress in the Reynolds equation arises from the mean momentum flux due to the fluctuating velocity. The mean momentum flux. This is the mean momentum flux. The Reynolds stress coming in the Reynolds equation, the Reynolds stress in the Reynolds equation arises from the mean momentum flux, which is the momentum flux here, and this is the Reynolds stress. So that's that additional momentum flux resulting from Reynolds stress in a turbulent flow. So that's the point I want to make. Now that takes us to this new discussion of what we call the closure problem. So if you remember, when we started discussing turbulence in one of the first classes, we talked about turbulence being one of the most unsolved problems in classical physics. And that is primarily due to this issue of this closure problem. What do I mean by that? So in math, a closure problem has to do with having more unknowns than equations. And that is exactly what you have here. So let's take a three-dimensional turbulent flow. You have four independent equations governing the mean velocity field, so namely the three components of the Reynolds equations, and then together with either the mean continuity equation or the mean Poisson equation. We cannot take both, right? Because the Poisson's equation is derived based on taking a divergence of the Reynolds equation or the momentum equation and invoking continuity, which means you either take the Poisson's equation or the continuity equation. Either way, you have four independent equations, three components of the Reynolds equation and the Poisson's equation for pressure. And how many unknowns do you have? You actually have more than four unknowns. So that would be three components of U and pressure. So if the flow was not turbulent, you would not have the Reynolds stresses. You would have four equations, four unknowns. But now, because the flow is turbulent, you have what we call the Reynolds stresses. This is the closure problem. Because we have four equations, four and more than four unknowns, because of the Reynolds stresses, we have a closure problem. We have more unknowns than equations. Now let's specifically see how many stress terms are we talking about. So the Reynolds stress term are components. These are basically components of a second order tensor, isn't it? Ui, uj, mean, or which is uj, ui, and because it is symmetric. So just so that it is clear, it is u1 squared, u2 squared, u3 squared. I have u1, u2, u1, u3. Then I have u2, u1. These are all, of course, mean. u2, u3, mean. u3, u1, mean. And u3, u2, mean. So a second order tensor, 9 components. And since it is symmetric, u1, u2 is equal to u2, u1. Of course, u2, u3 is equal to u3, u2, and u3, u1 is equal to u1, u3, me. So, because it is symmetric, essentially you have 6 components that are unknown. It started with 9 components being a second order tensor, but because it is symmetric, you have 6 components that are unknown. So the Reynolds stress tensor is a symmetric tensor. And now we know how the off-diagonal components are equal to each other because of the symmetry. Now let's think about the diagonal components. I have u1 squared, which basically comes from u1, u1, isn't it? u1, u1 or u1 squared, and then u2 squared and u3 squared, which are essentially the normal stresses, while the off-diagonal components are the shear stresses. So here, this right here are like the normal stresses. It's like a pressure term. It's a scalar. Whereas u1, u2 are shear stresses. Because in a stress term, generally the diagonal components are normal components or normal stresses, and the off-diagonal components are shear stresses. This is what you would have in a regular stress term, right? And that is what we are trying to equate that to a Reynolds stress tensor as well, just like we would do for example, a viscous stress tensor. Now, the turbulent kinetic energy is defined to be half of the trace. How? Because K will be half times u1 squared plus u2 squared plus u3 squared. This is how turbulent kinetic energy is just defined, right? Per unit mass, by the way. In that sense, the turbulent kinetic energy would be half u dot u, mean, in a turbulent flow. The turbulent kinetic energy is half mean u dot u or ui ui. So this is the trace of the Reynolds stress tensor, isn't it? This is the trace of the Reynolds stress tensor, because what you have here is half u1 squared plus u2 squared mean plus u3 squared mean. That's what you have. This is for any flow. This is the definition of kinetic energy. This is for a turbulent flow. So keep that in mind, right? So the mean kinetic energy per unit mass in the fluctuating velocity field, because you have a turbulent flow. In the principal axis of the Reynolds stress tensor, which is the diagonal component, the shear stresses are 0 and the normal stresses are the eigenvalues, which are non-negative, of course, because u1 squared mean is always going to be greater than 0. So it's non-negative. So in that sense, the Reynolds stress tensor is symmetric, of course, we saw that, and it is positive semi-definite. Positive semi-definite because the principal axis components are positive, are always positive. So those are some of the features of the Reynolds stress tensor. Now, let's go into the anisotropy related to the turbulent flow. So you can make an intrinsic distinction between the isotropic and anisotropic stresses. So the isotropic part is the diagonal part. So if you think about it, the isotropic stress, if I write it as 2/3 k delta ij, that comes about because you are writing it as the average of all the diagonal components. Are you getting me? You are writing it as the average of all the three diagonal components. That is why the 1/3 comes into play. And then you are writing it as 2 times k because you want to express it in terms of the kinetic energy. Otherwise, it would just be in terms of the velocity, the fluctuating velocity. So how did we define k earlier? We defined k earlier as half ui. We are doing that because, so now we are writing 2/3 k. The 2 times k comes about because of the ui can be expressed as 2 times k from here. Can you see that? The ui is 2 times the kinetic energy. That is where the 2k is coming from. And 1/3 because you're taking an average of all the three components. So that is how you would define an isotropic stress, the diagonal components. The anisotropic part is the off-diagonal components. This is for any stress tensor. The isotropic part is your diagonal components. So when we write the stress tensor in fluid mechanics, nothing to do with turbulent flow. When we write the stress tensor, the diagonal components is the normal stress or the pressure, and the off-diagonal components is the viscous stress. So that would be the shear stress or the tangential stress. So you have the normal stress and the tangential stress. So isotropic is the diagonal component and anisotropic is the off-diagonal component. Now here I am expressing it in terms of kinetic energy just so that I can remove the velocity and express it as a scalar, 2/3 k delta ij. And now if I write the anisotropic part, which is the deviatoric anisotropic part, I have aij equals uj mean minus 2/3 k delta ij. Now, why am I doing that? So if I have uj mean minus 2/3 k delta ij, see what happens when I is equal to j. When I is equal to j, delta ij becomes equal to 0 when I is equal to j. So the second term on this equation will just go to 0. Then you have, when I is equal to j, delta ij would be equal to 1 when I is equal to j, and delta ij would be equal to 0 when I is not equal to j. So in this equation here, when I is equal to j, this term becomes just 2/3 k, and then you have u1 squared minus 2/3 k. So then you will get your anisotropic part to be 0. That is exactly what you want. When delta ij is equal to 0, as in when I is not equal to j, then you are left with just uj, which is the anisotropic part, the off-diagonal component of the tensor. So what we are trying to do is we are trying to write the Reynolds stress tensor as an isotropic part and an anisotropic part. So you have aij as uj mean minus 2/3 k delta ij. So the isotropic part and the anisotropic part. Now if I normalize the anisotropic tensor, then and I write this, bring on this new variable bij, which is aij over 2k. I'm normalizing it by 2k. What I end up getting is I divide this equation by 2k and I get uj. Now since I used the notations I and j, I'm using a different notation, and since it's a free index, I can easily use ul. So write the kinetic energy as ul, and remember 2k is ul mean minus 1/3 delta ij, because the 2 went away because you divided it by 2k. So I have 1/3 delta ij. So that is my normalized anisotropic tensor. And then I can write the uj as 2/3 k delta ij plus aij. That is coming from here directly. So ui uj is 2/3 k delta ij plus aij, and then instead of I factor out a k, so I factor out a 2k, and then I have delta ij plus aij over 2k, which is 2k times delta ij plus bij, isn't it? So now what I have done is I have written the Reynolds stress tensor as 2k delta ij plus bij. The 2k delta ij comes about as the isotropic part, and this is obviously a normalized version of the anisotropic tensor. So now what I'll do is, if I consider the derivative terms related to pressure and the Reynolds stress term in the Reynolds equations. So going back to the Reynolds equations here, actually an easier version is, in here I have del xi of p delta ij. So del xi of p delta ij becomes the Kronecker delta makes the derivative del xi as del xj. And then I have del xi of p minus del xi of ui uj. So that term, if I just take those two terms, and now I'm going to write it in terms of the anisotropic stress tensor, then I have rho del xi of ui uj coming from the Reynolds stress term, and then as you can see here, this is del xj. Because the Kronecker delta made it a del xj. It was originally del xi, but because you had the Kronecker delta in, now it has made it a del xj. So you have a del xj of p is equal to rho. Now what you're doing is you're writing the Reynolds stress tensor as this part here. You're substituting this here. 2k 1/3 delta ij plus bij. So here we are writing it in terms of just aij, not bij. So it is this equation that we are going to be using. So then I will write the Reynolds stress as rho del xi of aij plus del xj of p, and I group, look at what I've done here, I group this 2/3 rho k along with p. Instead of the 2/3 k delta ij, this delta ij, Kronecker delta, is also going to make this del xi as del xj. Keep in mind, just so that you understand, del I delta ij, okay? Del I delta ij is del j. Basic rule, right? The Kronecker delta switches the derivative index. So you have del I delta ij is del j, and that is what is happening here, where I have del j of p plus 2/3 rho k. So what has happened here is I have grouped this kinetic energy term to the pressure term, and I have written the anisotropy term separately. That makes sense. The pressure to me is isotropic. The diagonal components in the Reynolds stress tensor is isotropic. So why not combine the isotropic part of the traditional stress tensor and the isotropic part of the Reynolds stress tensor? So then you have one big isotropic part in here. So this is isotropic, and this is anisotropic. So what we have done is we have absorbed the 2/3 k into the pressure, and now we can call this the modified mean pressure, because all it is doing is it is bumping up the pressure, because it's an isotropic term. It's a scalar that can be absorbed into the pressure. So this can be like a modified mean pressure. So for instance, you can call it a PM. Okay, I'm just using a notation here. PM is, and this is mean, PM is mean P plus 2/3 rho K. This is it. So what ends up happening is this Reynolds stress term, pressure gradient, can be written as rho Aij del xi plus del xj of PM mean. So what happened here? You have expressed the Reynolds stress term in terms of just the anisotropic tensor. We are trying to isolate the terms that matter. From the Navier-Stokes equations, we came down to the Reynolds equations, where we realized that the only term that is in addition to what we have generally for any kind of flow, including laminar flow, the only additional term is the Reynolds stress term. And even the Reynolds stress term, we are trying to isolate certain parts of it. What we did was we split it into the isotropic and anisotropic part, and the isotropic part could be absorbed into the pressure. That showed us that the anisotropic term is what is responsible for all the effects that we see in turbulent flow. That is the conclusion here. It is not the overall Reynolds stress term, it is the anisotropic part of the Reynolds stress term. So I hope that was clear. In the next class, what we'll do is we'll start to look at irrotational motion and more going into the symmetry associated with this Reynolds stress term. Thank you.